Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. So, today we will finish, starting from this, I will show you what we mean by Fermi liquid behavior for this self-energy and how it comes out. Then I will show you some experiments to make the contact between all these calculations and what is observed. Unfortunately, I will not do all the integrals and everything because, as you see, it's a big job in itself, right? So I hope that you will be happy that I show you how it's done in principle, and then in the end, it's doing some complicated integrals. Okay, and then I will show you how to compute the free energy in principle, or the grounds, but I will not do it because well, I will show you the formula, but I will not compute any free energy. And finally, we will move to lattice electrons. So we put the lattice back, and then we have a whole set of new problems. So we will work with the screened interaction that leads to the Hubbard model, as I will show you. And if we go to the lattice, in other words, we include the presence of discrete atomic sites instead of a uniform background. We go to a density functional theory that I will comment on later. So for now, all these things that we did for the free electron gas in the Gellium model is already a good approximation for metals that are on top of the periodic table, like sodium or aluminum or something like that. I will show you results. But as we go down and as we want to be more realistic, get more quantitative agreement, we need to take into account the lattice. So, are there questions? Okay, so I start with this famous delta function that I mistreated last time. And what we do, we want to show that this goes like omega squared plus pi t squared. So first, the idea is to change this integral over d cubed q over 2 pi q into an integral over d squared q perpendicular 2 pi squared times dq parallel over 2 pi. So what do we mean by q parallel? Well, there's a vector here. So this is, we will take this at the Fermi wave vector. So there will be the Fermi wave vector. And then there's a q that's parallel to this, and there's a q that's perpendicular. So locally, we have a coordinate system where we look at the q parallel and q perpendicular. Then the delta function, I write as the delta of omega plus omega prime minus kf squared over 2m plus kf dot q over m. And the idea here was precisely to be able to replace this by q parallel, and then I get plus q parallel square over 2m plus q perpendicular square over 2m minus the chemical potential. Okay, and since I do everything at 0 temperature, then I can this simplifies, and now I can solve for q parallel. So q parallel obeys the following equation. This is V Fermi. So V Fermi times the q parallel plus q parallel squared over 2m is equal to omega plus omega prime minus q perpendicular square over 2m. Okay, and so now if I go back to this expression, I can do the q parallel integral. I just have to remember that the solution of q parallel is this, okay? So I do the integral over q parallel, and here I'm left with d square q square. Then there's the pi here disappears with this. And the 2 survives, so that's why I still have a 2 here. No space to put it. And then when I do the integral over q parallel, I have to change the delta function. So here I have the v Fermi. To v Fermi, that's v Fermi is this. And I got rid of the pi, okay. And now I don't have the delta function anymore. I've done the integral over q parallel, and I'm going to put back the integral over omega prime. I'm sorry. So I have an integral, and then I have d omega prime over pi here. And this, I'm putting all these factors, but you will see very soon that they, I will butcher them. So here we have q, this is a function of q perpendicular, a function of q parallel that is a function of q perpendicular, omega, and omega prime. Okay? You see the q parallel is a function of omega plus omega prime and q perpendicular. That's what I've written here. And it's a function of omega prime. Very important. And then this is squared. Okay, and now I'm not going to work out all the prefactors and everything, but in principle we can just do this integral. But there's a nice approximation that we can do that is very accurate, and it is to consider that omega and omega prime, we want to delimit where omega is small. And we will see that because of these functions, if omega is small, omega prime will be small as well. Small with respect to what? With respect to the Fermi wave vector. Now, what is the scale of this q perpendicular and this q, well, this q perpendicular, yes. The scale is the Fermi wave vector, right? We can integrate over the whole thing. So it means that I'm comparing something that's of order of the Fermi energy with this is very small. So you can think of Fermi energy, let's say that 1 or 10 electron volts. And here I'm looking at the room temperature. So it's 1 over 25 electron volt. Okay, so there's a huge difference between this and this. So the idea is that I can neglect the omega and omega prime dependence that is here. So I'm just left with the omega prime dependence. And now you remember that chi double prime was an odd function of omega prime. Okay, and again, this integral over q perpendicular here varies over the Fermi Fermi wave vector. So it means that the omega prime, I can take just the linear part of this. So in other words, if I divide this by omega prime and I multiply by omega prime, this whole thing here, this except this, even the the omega prime. I should put here to be sure that I. So this integral is this omega prime over pi. So to make sure that I mean, this piece here has an omega prime dependence, but all of this I can neglect the omega prime dependence because this is linear in omega prime. If I divide by omega prime, I get a constant. And this approximation will be bad, but just when omega prime is on the scale of the Fermi energy again. Okay, so if we accept this, then I can get, I won't get the prefactor, it's a mess, but there's an exact expression. But I get the rest, I get the Fermi liquid. So this integral over omega prime, both function, Fermi function times omega prime, you can look up in books on integrals, or you can use some software. And in other words, it's an integral that can be done analytically. And the result is the result that we want. In other words, this integral times this, but this guy I take outside. This is proportional to omega square plus pi times the temperature square. So you see there's a sort of leftover of Matsubara stuff, where frequency goes like pi t. And one way to see the omega square here is to, like I said the other time, is that if I look at the function of omega prime, the Bose function and Bose here and Bose is 1 over exponential of beta omega minus 1. So we're working in the zero temperature limit, so beta goes to infinity, which means that when omega is negative, this is 0, and I get n Bose is minus 1. So I get minus 1 here, and then 0 on the other side, because when omega prime is positive, this is 1 over infinity. Now, if I look at the Fermi function is 1 when this is negative, and it's 0 otherwise. So if I'm looking at positive omegas, positive omega, yes. So when omega prime reaches minus omega, the function here, the Fermi function, f goes to 0. So I have 1 here, which means that the sum of the two functions is just the sum of the two functions is just this. So 1 here. And the window here, what is the window? The window is omega. So I'm integrating omega prime from 0 to omega and d omega prime. So that's proportional to omega square. Okay. You can put 2 if you want. So this is how Fermi liquid comes out. Okay. Now let's look at experiments. And it is the sigma double prime is negative, like we want. So I will first show you the result of a calculation for the jump in the Fermi. We saw that n of k in an interacting system. This is the expectation of C dagger K, Ck. Instead of being just a Fermi function, it's equal to this. And the height of this is Z. So what is Compton scattering? Compton scattering is that you send a photon, a high energy photon, and the photon comes out, and the electron does this. So you go from K to K plus Q. So when it's done in vacuum, this is in fact one of the first experiments that convinced people of quantum mechanics, because this really behaved like billiard balls. So in other words, there's a photon with some momentum and some energy that comes out with momentum and energy that you can measure. And you can do that for the electron as well. And you see that they behave really like particles in this experiment. Now, in our case, what will happen is that there will be a discontinuity here. The energy here transfer, the energy transfer Q. So there's some momentum transfer Q. I said energy, but for photon it's the same. So the momentum transfer Q here is big enough that this will always be outside the Fermi surface. But to be able to scatter, we need to have something inside. We need to be inside the Fermi surface. We need to have some K and then some K plus Q. So if you look at the cross section, there will be a discontinuity in slope that's related to this Z. In other words, the cross section will be proportional to integral d cube K over 2 pi cube of n of K times delta of omega minus epsilon K plus Q minus epsilon K. So you can work out. I mean, I won't do it. I mean, anyway, the results of the experiments are not so great, and I'm just working out all the details. But here it will depend on the final result will depend on the momentum transfer Q, like this. It would be m over Q times epsilon Q minus omega. You can see it here because this again will give K dot Q, where there's a cosine, so we do the cosine integral. In the end, the result depends on this. So let me share my screen to show you the results of these experiments. Okay, so here, this is the calculation. Okay, for n of p here instead of k, but n of p, and you see that when p is equal to k Fermi, there's a jump, and this, as you see, these are very old calculations. Bosco was at the University of Toronto, and so in the RPA approximation, you can calculate Z. We know how to compute self-energy, so we can compute Z, and you see how it depends on RS. And this is what I was working out here. So the final result depends on this quantity, like this. So kf squared minus q squared, and there's a theta function that comes from the fact that the integral is from q to infinity, and so this is the result for the non-interacting. The calculation I had above was with the non-interacting system. So for the non-interacting system, you get this dashed line, and there was this theta function. Okay. So in other words, here I assume that n of k was cut off at k. And this is the experiment. And the experiment is done for sodium. And now this is not the non-interacting case. This is really comparing theory and an experiment. And the result is not great here. But what's important is that there is indeed a jump, not a change like predicted here. There's a discontinuous slope at K Fermi. And this remaining cross section here is just telling us that there are states that are occupied above K Fermi, contrary to the non-interacting case. And so we see these occupied states here. Now, this is the mean free path. So the mean free path, excuse me. So the mean free path is computed simply from the imaginary part of the self-energy times the Fermi. So that gives the scattering rate, so the scattering time, and if we use the Fermi velocity, that gives the scattering rate. So this is the calculation from RPA with these are the crosses here, and the experiment are these open symbols here. And Plasmon theory just means that you take into account just a single peak in the susceptibility. You just assume that everything is in the plasmon. I think that's what it is. I'm not sure. And this is for aluminum, so you see it doesn't work that bad. And then this is not a calculation. This is just a measurement of the electron energy loss spectroscopy. And we saw that it was proportional to the imaginary part of 1 over the dielectric function. So this is for nanoparticles. And here the nanoparticles are big enough that you see, so the peak here can come from elastic scattering or other low frequency contribution. These small things that have been blown up are surface plasmon. But here the particles are big enough that there's a bulk plasmon here at 15 electron volts roughly for aluminum. And you can see the 2 plasmon peak here at 30 electron volt. So you see the scales are really big here for the plasma oscillation. And clearly, as the particles get smaller and smaller, that's their radius here, then you basically lose the plasmon peak. It becomes something that's related to small systems. Okay. So that's not a tremendous success, but it's for a simple-minded theory like this, it's not so bad. Excuse me. So I will give you just a few. We can see how to compute the free energy. It's very, very easy. And it's so-called coupling constant integration, and it's a very common trick to compute the free energy. So there's an integral to do. The free energy is more complicated to compute the susceptibility or free energy and self-energy. And basically it's because entropy is not easy to compute. So, but even if there's no entropy, actually, even the ground state total energy can be a mess. So we know that Z why am I writing in red? I don't know, but okay, let's do that. Z is equal to a trace of e to the minus beta, and then I will write h0, and then I would put some lambda. You will see what's the lambda equals 1 is the physical result. So I get lambda v minus mu n. So if I compute d log z d lambda, what is it? It's equal to 1 over z, clearly, times the trace of e to the minus beta h0 plus lambda v minus mu n. And now, now this whole thing commutes with itself. So I can, you know, work with all this as if it was an ordinary exponential. So I can put this whole thing down and differentiate with respect to lambda. So what will happen? I will get a minus sign. I will get a beta that I can put here, and I can there will be a v here. When I differentiate, it's just v that will survive there. So,
but then v doesn't commute with the thing in the exponential.
Well, there are two ways to see what happens. One way is to see that, okay, this I can I can write that e to the minus any operator. Okay, let me write the w operator divided. W is a function of lambda. So this is equal to e to the minus w of lambda times dw d lambda.
I mean, is it only true when so dw over d lambda commutes with w?
And well, okay. Another way to see this, which is more convincing, is that assume that you do a power series expansion of the beta. Okay, of the exponential. You do power series. Now, if I have h0 plus lambda v minus mu n times h0 plus lambda v minus mu n. Okay, I want to isolate everything that's related to v. Okay, but now you see that I have indeed I have h0 minus mu n times lambda v from that side, and then I have plus lambda v times h0 minus mu n, and they don't commute. Okay, but it's in a trace, so I can always all the lambda v's to the right.
Oh, that works for order 2, but then for order 3 that doesn't work anymore.
No, it works also. You can check.
Okay, I can check that. Okay, right, thanks.
You can check it recursively. Okay, there's another way to see it, which is to go to the interaction representation. Then you can do the derivative. Excuse me. And you can work it backwards. Okay, so given this, oh, I'm running out of. Okay, I have a new one here. I'm erasing so much today. I have some problems. So, so you see now that what I can do, this is the free energy, you know, minus kT times log z is the free energy. So if I do the integral from 0 to 1 d lambda of this guy here, minus 1 over beta d log z d lambda, this is equal to minus 1 over beta times the log of z minus 1 over beta times the log of z0. Because at lambda equals 0, I have the non-interacting value. And on the right-hand side, what do I have? I have the integral from 0 to lambda, d lambda over lambda times the expectation value of lambda v evaluated in the lambda theory. So you see, if I multiply by lambda here and I divide by lambda, that's what I did. This is 1 over lambda. And this here is okay, because there's some lambda dependence here as well. So this whole thing is really the electron gas theory, but not with the charge e square, but with a different charge. Okay, lambda times d square. So I have to do the, I have to compute this, but that's the potential energy. This is potential energy. I know how to compute potential energy. This is psi dagger, psi dagger. It's related to susceptibility, charge susceptibility. So I have to compute this, but with a different value of the electron charge. I just put lambda times d square, and I have to integrate over all these theories. It turns out that with RPA, it's rather easy to do, actually. I have done it in the notes, and because it has just has this form where you have a denominator, you have v square, vq, which is really e square over just a lambda times d square, and you integrate 1 over lambda, it will give you log of imaginary part of logs, and it's I mean, you can work it out. It's really easy for RPA but it can be done numerically also if you happen to be able to do this calculation only numerically. And you have to remember that this potential energy is also, we saw, it's also trace of sigma g, or it's also related to the charge susceptibility. So you have several ways of computing this, and you can do this integral either analytically, like in the case of RPA, or numerically. Okay. So I have log z is equal to the whoops, I have a clear sign mistake here. So I have the free energy is equal to the non-interacting free energy plus this coupling constant integration. I think this trick is due to Pauli. I'm not sure, but and it is widely used. And in fact, there are several ways of computing this quantity, and in a theory that I will show you in the Hubbard model that's called two-particle self-consistent. I had one of my students who has worried about these calculations of energy or free energy, and there are several ways to do them. Several approximate ways of doing them in an approximate theory. And this coupling constant integration seems to be the one that works best when you compare with exact results. Okay. Now, let's go to the real stuff, the density functional theory. So, when there is in the real system, there are lattices, and the density functional theory that I will show works very well for the elements that are on the top the top rows of the periodic table. And there used to be two different worlds. I mean, the world of density functional theory, electronic structure, and the world of people doing models like Hubbard model. But nowadays, actually, there's sort of a marriage between these methods. I mean, we can sort of, there's some realistic aspects to the models, a Hubbard model, for example, some realistic aspects that are missing. And similarly, density functional theory has some correlation effects that are missing. So what do I mean by correlation? Well, it depends if I talk to a chemist or to a physicist. Okay. So for a chemist, correlations is any effect that goes beyond Hartree-Fock theory. For a physicist, correlations is anything that goes beyond density functional theory. Okay. So the birth of density functional theory is related to Walter Kohn. And I mean, I won't, it's more of a distraction than anything. I can tell you more, those who are interested outside of class, but Walter Kohn was a prisoner in Sherbrooke during the war. Because he was Jewish, he was arrested. He flew to, in complicated circumstances, he flew to England, but then the English were, he was Austrian, so the English were worried about anybody that was not English, so they arrested him, and they sent all, not only him, but basically anyone that was not British, and they sent them to prisoner camps in the elsewhere in the empire. So it ended up being in the case of Walter Kohn, he was in Farnham, Trois-Rivières, and Sherbrooke, and he won the Nobel Prize. And actually, there were, I think, two or three of the people that were in these camps that earned the Nobel Prize. So not because you end up in the prisoner camp. That, in fact, it's in this prisoner camp that he first learned about science, because McGill University was teaching actually high school to these war prisoners, so they were not mistreated. So. So density functional theory, what is this? So the idea I will show you, it's based on the variational principle. So let me remind you how the variational principle works. So if we look at the expectation value of psi h psi, then this psi is some random wave function, and we take the expectation value. We can expand the wave function psi. We can expand in some eigenbasis. Okay, so I sum over I, AI times some eigenfunction of the eigenfunction of the Hamiltonian, okay, eigenenergy. So these are the true eigenenergies that I don't know. Actually, in the notes, just to be consistent in the notes, I use a shorthand here. I just used I. So, so I don't know what are these eigenenergies, but they exist, okay, these eigenfunctions. So if I do this product here, I will be left with sum over ij, a star I, aj, times phi I times ij. I tried to be short, and I'm wasting time in using a long notation. So I have I j times e I, and this is delta Ig, right? Because by hypothesis, these are energy eigenstates. So I'm left with sum over I of AI squared times EI, and this is necessarily greater or equal to sum over I AI squared times the ground state energy. Okay, because by hypothesis, the ground state energy is smaller than any of these energies, and because the wave function is normalized, then I have to write some normalized wave function here. The sum over AI squared is 1, so this is E0. Okay, so it means that I have established that this is always greater or equal to the ground state energy. So the ground state energy is the minimum of this over wave functions. Okay, so that's the variational principle, very easy. So this is always greater or equal to the ground state energy. So we start like this. We say that we want to say that the ground state energy E well, here I wrote E0, so let me write E0 is equal to the minimum over all wave functions over psi of this guy. But what is this? This is the psi, and then I have the kinetic energy operator that I will write like this, take kinetic. I have the Coulomb interaction that I will write like this, the C. And then I have the lattice the effect of the lattice, okay? And then what is the effect of the lattice? What is this? V lattice is equal to integral d cube r d cube r prime of wave function, and here I have psi dagger r psi r times z e squared over 4 pi epsilon 0 times the absolute value of r minus r prime times n lattice of r prime. Okay, so you see, if I z is not z, the z I've used up to now. It's just the charge of the protons or the nuclei that are there. So I can put this charge into this density here. Okay, this is the delta function at various places in the network, and then I have a psi. Yeah. So if I call this integral over r prime I can take it outside this, because I'm looking at the electron wave function, and this is just the position of the ions, and I'm assuming here, you understand, I'm assuming that the ions are not moving. I don't have the kinetic energy of the ions here. So the kinetic energy of the ions will lead to phonons, and we can introduce them later. So we start by having some this. So it means that now what is this? The wave function times this. This is the electronic density. You agree? So this whole thing I can write as integral d cube r of the electronic density n of r times v lattice of r. Okay. If I do the integral over r prime, you see that I get just a function of r. Is it okay? I get the influence of all the ions here at position r. And it interacts with the density of electrons at position r. Very important. Okay. So so I'm left with this. So this proof, the original proof is starts with Owenberg and Kohn, and this proof is due to Lieb and Levy, and I think I like it. I like it better. So and I get plus this guy plus integral d cube r n of r vl of r. Okay. Now this I'm going to do the minimization step. Okay, the n of r here still depends on the wave function. Huh? So it's included in the minimization. But I will do the minimization in two steps. I will say that it's the minimum with respect to the density n of r. And now, okay, and then there's the minimum with respect to all the wave functions that lead to the same density n of r. It's certainly something complicated, but in principle, it's perfectly fine, right? I do the minimization in two steps. Instead of minimizing over all the wave functions, I minimize over all the wave functions that give the same density. And then I minimize with respect to density. Okay. So this function I can write as minimum n of r. And this function will be a function of density, okay, because I minimize over. This does not depend on the position of the ions. It's just something related to the electronic wave function that is constrained to have a certain density n of r. Okay. So it's the minimum with respect to n of r of this functional of the density. Okay, because this is again a function, and this now becomes a number. So that's the definition of a functional. Plus integral d cube r n of r vl of r. Okay, so what have we established? We have established that the ground state energy E0 is a functional of VL. Okay, because I'm minimizing with respect to n of r. Now, you see, this is like a Legendre transform. This is like, if you want, this is like energy equals to free energy minus plus T times entropy. So free energy is a function of T, and you minimize with respect to T this guy. So it will give you that energy. So this is a function of entropy. And the derivative of the energy with respect to temperature, with respect to, I'm sorry, to entropy, is equal to temperature. Okay, so that you get dE equal TdS minus PdV, and the temperature is the derivative of the energy with respect to the entropy. So the energy is the Legendre transform of the free energy, and the free energy is the Legendre transform of the energy. So here we have exactly the structure of the Legendre transform. So it means that and I assume here that the ground state is unique. Okay, so there is only one ground state. So I have that the functional derivative of the energy, that's a functional of V of L, with respect to VL of R is equal to N of R, okay? That's the only contribution. So in principle, I can invert this equation, and now I can write the energy. The energy can be written as a functional of the density. So that's really great progress, actually, because you see the wave function is complicated. It has many, many components and so on. But there's a theorem that I just showed based on the variational principle that shows that the ground state energy can be written as a functional of the density. Okay. So up to now, this is a good example of a result that is exact and apparently useless, because it's we need to find this function and so on. So what is what makes it the practical thing is the approach of Cohn and Sham, which I will not have time to show, but I will show you how it starts. So the idea of Cohn and Sham is to, say that I will parameterize the density N of R as sum over orbitals, and I will have N over 2 orbitals if there are N electrons, and I'm always working at 0 temperature here, and sigma spin of the square of phi I of R. Okay, so up to now it's just a way of parameterizing the density using orbitals. These are called the Cohn-Sham orbitals. So this is a non-interacting problem, but you see, it's just a parameterization of N of R for now. But the usefulness of this is that I can, now the kinetic energy is easy to compute in that basis. Okay, the kinetic energy, T Cohn-Sham, will be equal to integral d cube R of sum over, and I have to sum over I Cohn-Sham kinetic is equal to this d cube R phi Cohn-Sham. So here we will work with real orbitals anyway, so because for now, I don't, time reversal symmetry is not broken, so I can use always real orbitals. So phi of r times minus rad square over 2m times phi cone sham of r and I. Okay, so that's, I can do that. So now the idea will be, I will show you that how we approximate this object here. This is the whole problem, right? But we know its definition, right? F of n is just this. So this whole thing here is f, the functional of n. So here I have shown that E0, oops, the functional of n, but what I mean by this is this, right? I do this and I invert and I find v as a function of n. In other words, for every v of L of r, there's a single n of r. And vice versa. For every density, there's a single v of L. That was the content of the Hohenberg-Kohn theorem, but is derived in the notes and is not very complicated. Okay, so now the program would be to minimize, instead of minimizing with respect to n of r, we will minimize with respect to the Kohn-Sham orbitals. Okay. So I have enough freedom in these phi. I can take whatever I want, as long as they are normalized. I can take anything I want and get any density I need. So we transform this as minimization with respect to these orbitals. And that's the same as Hartree-Fock theory for electrons. Okay, so we will stop here. It's already very late. And do you have any questions? So in the notes, I made a mistake in writing this approximation of V of n, but I will put some updated notes right now. Okay. So see you Friday then.
Merci, bonne journée.
Okay. Merci, bye-bye.
Merci.
Thank you. Bye.
Bye.
Thank you. Bye-bye.
Thank you. Bye.
Bye, thank you.